Assalamu alaikum. In this video, we monitor hardware performance counter by analyzing memory consumption and cache by using three different machine learning algorithms. Number one, k nearest neighbor. Number two, logistic regression. And number three, random forest. These algorithms are implemented in Python language. We check which algorithm of machine learning is suited with respect to our hardware performance. We consider two hardware performance counter. One is memory consumption and the second one is cache. Cache is a location in our hardware which stores the data temporarily. Access of data is easy in cache due to which it makes the hardware faster. The CPU performance is depending on the RAM of the computer. As more as the CPU accesses the RAM, it makes computer faster. In this video, we use the system Intel Core i5 and the version of the operating system is Ubuntu 20.04.1. The simulation is tested on Ubuntu on the terminal by running various built-in commands. First, we used the Valgrind tool to generate the memory traces of three machine learning algorithms. We start from k nearest neighbor. First, we generate the memory traces of k nearest neighbor. The execution time of k nearest neighbor algorithm is 8.11229. This is the output file of memory traces of k nearest neighbor. And for visualization, we use the Massif-Visualizer tool and it gives a detailed information in a form of graph that shows how much memory is used during the execution of the program. Now the massive.out file is generated. This graph shows the memory heat consumption of k nearest neighbor. In the graph, the x-axis shows the time and y-axis shows memory heat size. The graph shows that the k nearest neighbor consume 27.5 megabytes memory heat consumption. Now we generate the memory traces of logistic regression. The execution time of logistic regression is 330.2795 something. This is the output file of memory traces of logistic regression. And for visualization, we use the Massif-Visualizer tool, and it gives a detailed information in the form of graph that shows how much memory is used during the execution of the program. Now the massive dot or file is generated. This graph shows the memory heat consumption of logistic regression. In the graph, the x-axis shows the time and the y-axis shows the memory heat size. This graph shows that the logistic regression consumes 77.6 megabytes, megabytes memory heat consumption. Now we generate the memory traces of random forest. The execution time of random forest is 177.17. This is the output file of memory traces of random forest. And for visualization, we use the Massif-Visualizer tool. This graph shows the memory heap consumption of random forest. The x-axis shows time and y-axis shows memory heap size. This graph shows that the random forest consumed 1.7 gigabytes memory heap consumption. All the results clearly show that the memory heap consumption of k nearest neighbor K nearest neighbor has consumed less memory as compared to logistic regression and random forest. From the detailed graphical information, we conclude that the K nearest neighbor is fast and efficient algorithm as compared to logistic regression and random forest. Now we analyze the test results of cache performance by monitoring the access count, fetch count, prefetch count, hit rate, miss rate, and average access time on both L1 and L2 cache. We consider three replacement policies: LRU, PLRU, and random. Now you can see that it is the cache size, and it is set number, and it is associativity. Associativity tells where block has been placed. There are three types of associativity. Direct map: a block with a given address can only be placed in a single location in the cache. Fully associative: a block can be placed anywhere in the cache. And set associative: the cache is divided into the group of blocks called sets. Each memory address mapped to exactly one set in the cache, but data may be placed in any block within that set. For example, if we have two-way set SSD, means four set and two blocks. Now we have some replacement policy. Number one, LRU. LRU stands for least recently used. LRU replaced the block which was least recently used. PLRU stands for pseudo least recently used. Instead of using an exact measure, they use an appropriate measure of the recently used lines. This allows for much more efficient cache management. First, we run the cache simulator for k nearest neighbor. For L1, we fix the set number 2, associativity 4, and our cache size is 1024. First, we apply PLRU replacement policy. On L1, we perform prefetching. So here we write a use prefetch is equals to 1. 1 means prefetching is applied. On L2 cache, we fix the cache size 1024. Set number is 2. Replacement policy is PLRU. And on L2 cache, we did not perform prefetching. So here we fix use prefetch is equals to 0. 0 means without prefetching. Now we run this code. To run the cache simulator, we first run the make command in which we send the trace file. Here is the output. Now you can see that on L1 cache, the cache size is 1024 byte, set number is 2, accessibility 4. On L2, and you can see that on L1 cache, prefetching is applied. On L2 cache, the cache size is 1024 bytes, set number is 2, accessibility is 4. And here you can see that no prefetching is applied. And in both L1 and L2 cache, you can see that PLRU replacement policy is applied. Total L1 access count is 9842. Miss rate is 0.010616 and hit rate is 99.989 something. Total L1 fetch count is 1 and total L1 prefetch count is 8 because here on L1 cache prefetching is applied. Now L2 access count is 5. Miss rate is 100% and the hit rate is 0%. L2 fetch count is 5. Here L2 prefetch count is 0 because on L2 cache there is no prefetching is applied. And you can see that on L1 cache, the average access time of k nearest neighbor is 3.01177 cycles. Now we can change the cache size. We can change the cache size. We can also change set number. Accessibility is 4. Replacement policy can be changed. Now this time it is LRU. Now this time you can change that on L1 cache you did not perform prefetching. So here we write 0 instead of 1. Now on L2 cache you can also change the size 2024. Set number can also be changed 4. Replacement policy LRU. On L2 cache we perform now prefetching, so here we write 1. Now save the file. Here first we clean. Make clean command. Now we again run this code. Now you can see the output. On L1 cache, the size will be now 2024 byte. Set number is 4. Accessibility is 4. And now you can see that here replacement policy is LRU. And now you can see that on L1 cache there is no prefetching is applied. Now on L2 cache, the cache size is 2024 byte. Set number is 4. Accessibility is also 4. Replacement policy is LRU. And now you can see that prefetching is applied here on L2 cache. This time it is opposite. Now you can see that total L1 access count is 9842. 98042. On L1 cache, the average access time of k nearest neighbor is 3.01177 cycles. This rate is 0.010161 and hit rate is 99.989837. Total L1 fetch count is 1 and total L1 prefetch count is 0 because on this time on L1 cache we did not perform here prefetching. Total L2 access count is 1. On L2 cache, the average access time of k nearest neighbor is 110.00 something cycles. Miss rate is 100% and hit rate is 0%. Total L2 fetch count is 1. Total L2 prefetch count is 8 because on here L2 cache we perform prefetching. Now next time we can also change the cache size. Now we set the set number 8, accessibility 4, cache size will be 4024. Now this time replacement policy will be random. Now this time we perform on L1 prefetching, so here we write 1. Now on L2 cache, where we set the cache size 4024, set number will be 8. Replacement policy now will be random. Now this time on L2 cache we did not perform here prefetching, so here we write 0. Now save this file and again run this code. Now you can see the output. On L1 cache, here we fix the cache size 4024 bytes. Set number is 8 and associative will be 4. In this time, a random policy will be applied. On L1 cache, no prefetching is applied, so here it will be written P. On L1 cache, this time we applied prefetching, so here it is written prefetch applied. On L2 cache, the cache size is 4024 bytes. Set number is 8, associativity 4, random policy, and on L2 cache, no prefetching is applied. So here it is written no prefetch applied. Total L1 access count is 9842. On L1 cache, the average access time is 3.01117. Miss rate is 0.010161 and hit rate is 99.98 something. Total L1 fetch count is 1. Prefetch count is 8 because on this time on L1 cache prefetching is applied. Total L2 access count is 5. 5 and here miss rate will be 100 and hit rate will be 0.0 something. Or total L2 fetch count is 5 and total L2 prefetch count is 0 because L2 cache prefetching is not applied. Now we follow the same procedure for another algorithm which is logistic regression. On the restaurant version, we fix the set number 2. Cache size will be 1024. Here we apply PLRU policy. On L1, we apply file perfection, so here we write 1. On L2, here we fix the cache size 1024. Set number will be 2. Random policy will be PLRU. And here on L2 cache, we did not perform fetching, so here we write 0. Now save this file and run this code. Now you can see the output on L1 cache. The cache size will be 1024. Set number is 2, associativity 4. And here we apply PLRU replacement policy. And on L1 cache, you can see that the prefetching is applied. Now on L2 cache, the cache size is 1024 bytes. Set number is 2, associativity 4. Here, replacement policy PLRU is applied, and on L2 cache you can see that no prefetching is applied. Total L1 SS count is 9520. On L1 cache, the average SS time is 3.011555 cycles. Cycles, the miss rate is 0.0% and hit rate is 99.98 something. On L1 cache, prefetching is applied, so here it is written 8. On L2 cache, the average access time is 100 cycles and miss rate is 100% and hit rate is 0.0. And on L2 cache, the prefetch count is 0 because here there is no prefetching is applied. Now we done some changes in the code. Now this time we change the cache size 2024. Replacement policy will be LRU. Now this time we on L1 cache we did not perform prefetching, so here we are 0. The cache size will be 2024. Replacement policy will be now LRU. On this time on L2 cache we apply prefetching, so here we write 1. Now save this code and run this code. Now you can see that on L1 cache size is 2024 bytes. Select number is 2 sensitivity 4. Replacement policy now will be LRU. On L1 cache there is no prefetching is applied. On L2 cache, the cache size is 2024 bytes. Set number 2 sensitivity 4. Replacement policy is LRU. On L2 cache prefetching is applied. Now you can see that on L1 cache the average access time is 3.0115555 cycles. This rate is 0.01054 second. Hit rate is 99%. On L1 cache prefetching is not applied, so here it is 0 written. Total L to access time is 1. On L2 cache the average access time is 110 cycles. Miss rate is 100% and hit rate 0%. On L2 cache prefetch count is here because here a prefetching is applied. Now we apply the same procedure on random forest method. On random forest, on L1 cache we fix the size 2024. Set number is 2 associated with folder. Replacement policy is LRU. On L1 cache, now we perform prefetching, so here we write 1. On L2 cache, we did not perform prefetching, so here we write 0. Now we execute this code. Now we check the output. In random forest, on L1 cache, the cache size is 2024 bytes. Set number is 2. Associativity is 4. Now on L1 cache, we perform prefetching, so here we write prefetch is applied. On L2 cache, the cache size is 2024 bytes. Set number is 2. Associativity 4. On L2 cache, here we did not perform prefetching, so here it is written no prefetch applied. Total L1 access count is 9797. On L1 cache, the average access time is now 3.01122 cycles. On L1 cache, prefetching is applied, so here it is written 8. On L2 cache, prefetching is not applied, so here it is written 0. On L2 cache, the average access time is 0.00 something cycles. Now we change in code. Now this time we apply random policy. And this time we fix the cache size 4024. On L2 cache here we write 4024. We apply random policy. Here it also we apply random policy. On L2 cache we perform refreshing, so here we can change 1. And on L1 cache we did not perform fetching, so here we write 0. Now save this code and run this code. Now we check the output. On random forest, on L1 cache, the cache size will be 4024 bytes. That number is 2 sensitivity 4. Random policy is non-random. Replacement policy is non-random. On L1 cache, no prefetching is applied, so here it is written no prefetch applied. On L2 cache, the size will be 4024. Set number is 2. Replace policy is random. And on L2 cache, we perform prefetching, so here it is written prefetch applied. Acha. On L1 cache, the access count will be 9797, on L1 cache, the average access time is 3.0112 cycles. Miss rate is 0.0% and hit rate is 99.98%. On L1 cache, prefetching is not applied, so here it is written 0. On L2 cache, the average access time is 110.00 cycles. Miss rate is 100% and hit rate is 0%. On L2 cache, the prefetch count is 8 because here on L2 cache prefetching is applied. From all the results of cache performance of k-nearest neighbor, logistic regression, and random forest, we conclude that when we change the cache size or set number and replacement policy, it gives the same result on L1 and L2 cache. It only shows difference when different algorithms are applied on cache simulator as an input. As we know that the average access time stands for average access, as we know that the AAT stands for average access time, and average access time is the time the cache is accessed. From all the results, it is concluded that the average access time of k nearest neighbor is 3.011003 on L1 cache, and in logistic regression, the average access time is 3.011242 on L1 cache, and in random forest, the AET is 3.010983 on L1 cache. But on L2 cache, all the three algorithms show same average access time, which is 110. As from the results, we conclude that the logistic regression has large or greater average access time as compared to k nearest neighbor and random forest. So we can see that logistic regression has efficient algorithm as compared to others with respect to cache performance. Now I am conclude that with respect to cache performance, the logistic regression has large or greater average access time as compared to k nearest neighbor and random forest. So we can see that logistic regression has efficient algorithm. Thank you.